Using the standard reduction potentials listed in Appendix E, calculate the equilibrium constant for each of the following reactions. All right, so for the first one, we have iron losing electrons to nickel 2 to turn into nickel metal, and iron turning into iron 2. So I go to the reduction potential chart, look up the reduction potential for nickel 2, look up the oxidation potential, well, deduce the oxidation potential for iron, and add the two together to get the voltage for the cell. All right, so as we saw in the last problem, there's this relationship between the voltage at standard conditions, 1 molar concentrations, and the equilibrium constant. 2 moles of electrons are being transferred in this redox reaction. So divide that into the constant. That equates equilibrium constant to the voltage. I put in the voltage, positive 0.16 volts. So the expectation is I'm going to have a spontaneous K value. So rearrange the equation and solve for K. Same with B. Look up the reduction potential for H plus ion taking electrons. Look up the deduce the oxidation potential for cobalt. Add the two together and get the voltage for the cell. Again, we have a positive voltage. So when I plug it into the equation and rearrange, I expect a spontaneous reaction. C. 10 moles of bromide going to 5 moles of bromine, so that means 10 moles of electrons being transferred. Again, I have a positive voltage, right? So 10 moles of electrons being transferred. I rearrange and solve for K. Very spontaneous reaction. Consider the voltaic cell illustrated in figure 20.5, which is based on the cell reaction where zinc metal is giving up electrons to copper 2. Under standard conditions, what is the maximum electrical work in joules that the cell can accomplish if 50 grams of copper are formed? All right. So standard conditions, I can look at the reduction potential chart, get the reduction potential for copper, deduce the oxidation potential for zinc, and get the voltage for the cell at standard conditions. All right, so there's this relationship between the voltage at standard conditions and the free energy change at standard conditions. Right, if I multiply the number of moles of electrons being transferred by Faraday's constant, by the voltage at standard conditions, what I've essentially done is gotten a conversion factor now to go from kilojoules from moles of copper. All right, so if I wanted to make a mole of copper, this is how many kilojoules I'd have to release. So now I can use grams of copper in the molar mass to get to moles, and now I can use this conversion factor to figure out what the maximum work done in joules would have to be. So I'd have to release 167 kilojoules to make 50 grams of copper. A voltaic cell is constructed that uses the following reaction. All right, so zinc is giving up electrons to nickel 2 plus. What is the voltage of the cell under standard conditions? So I look up the reduction potential for zinc, deduce the oxidation potential, look up the reduction potential for nickel 2 plus, get the oxidation potential for zinc, and get the voltage for the cell. What is the voltage for the cell if I change those concentrations, right? I'm not at standard conditions. I've got a 3 molar concentration of the nickel 2 plus and only a 0.1 molar concentration of the zinc. Well, with these concentrations, I'm more towards the beginning of the reaction. I've got a higher concentration of reactants than I do products. So this is a fresher battery. So when I plug into the relationship between the voltage at non-standard conditions and how it equates to voltage at standard conditions, the expectation is I'm going to have a fresher battery. I'm going to have a higher voltage. All right, so 2 moles of electrons being transferred. I plug the concentrations into the reaction quotient. Concentration of the products, raise their stoichiometric coefficients, divided by the concentration of the reactants, raise the stoichiometric coefficients, and I solve. And as expected, my voltage is higher when I have a higher reactant concentration than I do product. I'm more toward the beginning of the reaction. So if before I did this, right, I ran the cell, right? So again, this is what we're doing. We're generating a voltage at non-standard conditions. 0.1 molar concentration of the zinc, that's the product concentration, and a fresher nickel concentration, right? 3 molar. All right, so with C, I have these concentrations, right? So with these concentrations, I'm further towards the end of the reaction, right? I have a higher concentration of the product than I do the reactant. So this is going towards the end of the reaction. So my expectation is the voltage is going to be lower when I plug into the equation. Of course, recognizing that when this reaction's over, right, when I've made as many products as I'm going to make, lost as many reactants as I'm going to lose, the voltage is going to be zero at equilibrium, right, the equilibrium concentration. So these are not equilibrium concentrations. I'm generating a positive voltage. This means I'm still sliding towards equilibrium. A voltaic cell utilizes the following reaction. Cesium 4 plus reacting with chromium. Okay, so what is the voltage for the cell under standard conditions? So I look those up. Look up the reduction potential for cesium 4 plus turning into 3 plus. Chromium's oxidation potential, get the voltage for the cell. B, what is the voltage for the cell when I have a 3 molar concentration of cesium 4 plus and a 0.1 molar concentration of cesium 3 plus? So when I plug into so I've got concentration of the reactants, and I've got concentration of both products here. That's what it is. All right, so same thing. I'm plugging into the relationship between voltage at standard conditions and non-standard conditions, so except I just have different values for the concentration of the products and the reactants. Different equilibrium expression, right? We always leave solids out, but I've got a coefficient there in front of the Ce4 plus. So I've got to raise the concentration of the reactants to the third power, divided into the concentration of cesium 3 plus, raised to the third power, times the concentration of chromium 3 plus. 3 moles of electrons being transferred here. So when I solve for the voltage at non-standard conditions, I get this. So I'm fresher, right? I've got a higher concentration of the reactants than I do the products. I'm at the beginning, more at the beginning of the reaction than the end, compared to standard conditions. So this is the voltage being generated by this cell with these concentrations. All right, so I changed the concentrations, right? I've got a lower concentration of the reactant, higher concentration of the products, so I'm more towards the end of the reaction. So when I plug into Q, take Q, take the log of Q, multiply it by the constant divided by 3, negative, subtract that from the voltage at standard conditions. The expectation is I'm going to have a lower voltage than standard conditions. I'm more toward the end of the reaction. So 2.21 as opposed to 2.35. So closer to equilibrium concentrations than at standard conditions. What is electrolysis? Electrolysis uses electrical energy from the surroundings to derive non-spontaneous reactions forward. All right, so if I want to create sodium from sodium ion, I've got to pump the electrons back onto the sodium off of something else. This is why we don't find, sodium metal on the beach. It's good because it bursts into flames as soon as it hits water. So how do you make sodium metal? Well, we'd have to use electrolysis. B, are electrolysis reactions thermodynamically spontaneous? No, we've got to actively pump energy in order to make them happen. I've got to raise the potential energy of the system. C, what process occurs at the anode in the electrolysis of molten? All right, so I've got to have it molten. I can't do this with aqueous sodium chloride because water gets in the way. Molten sodium chloride. So I melt salt. Takes a lot of energy. At the anode, I'm sucking electrons off a chloride and pumping them back onto the sodium metal. So again, this is the way we use voltage to make this non-spontaneous reaction spontaneous and raise the potential energy. So I actively drive the electrons back onto the sodium ion to make sodium at the cathode. All right, so the electrons are flowing towards the sodium ion and being pulled off of the chloride, which is making chlorine gas at the anode. D, why is sodium metal not obtained when I have an aqueous solution of sodium chloride? All right, water gets in the way. When you start pumping electricity into water, the thermodynamically easier one to do is suck the electrons off of oxide and pump them back onto H plus ion to make hydrogen gas and oxygen gas like we've done in class. So if I want to generate those gases using my my apparatus in class, I've got to actively pump energy in to make it happen. Oh, there's the answer, D. Sorry, I had to click through. Reduction of sodium cannot occur in an aqueous environment because of water. A chromium 3 plus solution is electrolyzed using a current of 7.6 amperes. What is the mass of chromium solid that is plated out after 2 days? So this is the way electrolysis problems go, right? We're trying to create chromium metal from an ore that contains chromium 3 plus. So we run current through and pump the electrons back into chromium 3 plus to reconstitute the chromium metal. So the new conversion unit we have here is amperes. Amperes is a measure of how much charge goes through the wire per second, right? So coulombs is a measurement of charge. So 7.6 coulombs for every second. That's the amperage we're using. So we ran the thing for 2 days. What we want to do is go from days to grams of chromium. All right, so first things first. If I want to use this conversion unit, it's a way to get out of seconds and get to coulombs. I want to go from days to hours, hours to minutes, and then minutes to seconds. Now, if I multiply by this conversion factor, I cancel seconds, and I've converted to how many coulombs I've had to generate for 2 days. Now I can use Faraday's definition to go from how many coulombs you have in 1 mole of electrons to get to mole of electrons. And now I recognize that it takes 3 moles of electrons to reduce chromium 3 plus. Use the molar mass of chromium 3 plus to get to grams. And so it's a big, long converting problem, right? With this amperage running for 2 days, I could generate 235.9 grams of chromium. All right, what amperage is required to plate out 0.25 moles of chromium from a chromium 3 plus solution in a period of 8 hours? Again, we have to have some sort of how long this has been running. And what I want to get to is the ratio, right? I want to get to amperage. I want to get to coulombs per second. So they gave me moles of chromium. For every 1 mole of chromium 3 plus, it's going to take 3 moles of electrons. Now I can use Faraday's constant to go from moles of electrons to how many coulombs I have. So I've got coulombs up in the numerator. What I need to get is seconds in the denominator, right? So 1 over hours, right? I ran it for 8 hours, from hours to minutes, from minutes to seconds. And when I multiply across, everything cancels except for coulombs per second. So that's the amperage that I have to use for those 8 hours to get that amount of chromium plated.